Hi there. Okay, so we're going to talk about section 6.1, sinusoidal graphs, essentially graphs of your sine function and your cosine function. So a couple things just right at the start of this section. It is so important that you read through the book in this section and work through the examples. They guide you through a bunch of different examples, and there's just really no other way than to sit and have a pencil and paper out and draw along with the examples that they're doing in order to help you learn most effectively. Okay, so far we've considered trig functions as ratios of sides of right triangles and also related to points on the circle. And one of the things that we noticed is that when we were looking at our trig functions on the coordinate axis, once we went one time around, i.e. 360 or 2 pi, it repeated itself. So that's how we had coterminal angles. So for example, if I have, say, a 45-degree angle, well, that's coterminal with 405 degrees. Okay, so, and I guess, sorry about that pause, but what I wanted to say there is, then the sine of 45 is equal to the sine of 405. Okay, it's a coterminal angle in the sense that once we go 360 degrees or 2 pi around, this is just going to start repeating itself again and again. Sometimes people like to think of Ferris wheels when they're talking about these sorts of functions. And when a function repeats itself from some point on, we say that that function is periodic, okay? Just like a clock, really. So what I want to say is that formally stated, a function is periodic if the function value at some x is equal to the function value of x plus p for all x, and p, which is greater than 0, is the period of the function. Okay, so we're really going to be looking at our unit circle right now. So we have 1, 0, 0, 1, negative 1, 0, 0, negative 1. And again, as always, pretend this is actually a decently drawn circle. Okay, so what I want you to recall is, notice we go around in the positive direction, that's counterclockwise. We can talk about going in the negative direction. That just means that we are going clockwise. Okay. Now, the other thing that I want you to recall is that on a unit circle, remember your sine is your y value and your cosine is your x value. All right. So what I want to do is I want you to note that for our sine and cosine, our period is 2 pi. One of the things that you're going to note is when we start chapter 6 and really start looking at the graphs of our functions, we talk about these things in radians more often than in degrees. So you'll notice that I'm going to now talk about a period of 2 pi as opposed to a period of 360 degrees. Okay. All right, so what I want to do is I want to show you what the graph of our sine function looks like. And one of the things that you'll know whenever we want to graph a function is that we need to take different values. Now we have some common values that we can look at here. And I'm going to use my unit circle in order to help us. Okay, so for example, the sine of 0 is 0. We know the sine of pi over 2 is 1. Remember, we're doing our sine, so it's our y values. The sine of pi is 0. Sorry about that. The sine of 3 pi over 2 is -1. And then when we're back at 2 pi, we get 0. Now, I also could have looked at this going in my negative direction. And you may ask, why am I talking about the negative direction here at all? Well, the reason why is when we graph on our Cartesian coordinate system, we have our positive horizontal and our negative horizontal axis. So same thing, I could go negative pi over 2, which we know is -1. Negative pi, we're at 0. -3 pi over 2, we're at 1, etc. -2 pi, we're back again at 0. So we can plot all of this now. Okay, and this is actually pretty cool how it looks. So one thing we notice is that our period is 2 pi. After 2 pi, my function's going to repeat itself. All right, so the other thing that I want you to note is that the radius of the circle we said is irrelevant for these functions. Our sine and cosine is completely dependent upon our angle. So one of the other things we see is that our range goes from -1 to 1. Okay, so I'm just going to put various significant tick marks on my graph. And notice if we want to, we could have continued going further, but I ran out of space. And besides, I'd like to go in the negative direction because I'll show you 2 periods of this function this way. All right, so we have that the sine of 0 is 0. When we're at pi over 2, we're up at 1, 0. I'm just plotting the points that we found here from our unit circle. Okay, I'm just plotting those points on my graph. And now if I play connect the dots, we get this beautiful sine wave. And it repeats itself. So we say that one full sine wave goes from 0 to 2 pi. All right, notice this came straight from our unit circle. All right. We're going to come back to that momentarily, but now what we're going to do is redraw our unit circle. And we're going to talk about our cosine. Okay, remember your cosine is your x value as we're traveling along our unit circle. So now if I want to graph the cosine, again, we know again that our period is 2 pi. Okay, that has not changed at all. So let's take our values here. When we're at 0 radians, our cosine is 1. When we're at pi over 2, we're at 0. When we're at pi, we're at -1. 3 pi over 2, we're at 0. And then 2 pi, again, we're back at 1. And as we did with our sine function, we can also go clockwise around the circle. -pi over 2, we're at 0. -pi, we're at -1. -3 pi over 2, 0, and -2 pi, we're back at 1. All right, and we can plot these again as well. Okay, so notice again that my range goes from -1 to 1. We have similar tick marks because these are our pretty significant angles when we're talking about our unit circle. Excuse me. And then we can go in the negative direction as well. Sorry about that. I have a cat who's really interested in my writing here. All right, now if I plot these values as above, we'll see we have our cosine wave. All right, so that's our graph of our cosine. Now, what I want to do is note some properties of our sine and our cosine graphs that are really important to note right from the start. Hold on one second. All right, so one of the things that I want to mention is as follows. Notice that they both have the same domain and the same range, okay? So what I'm going to note is that the domain of these functions, we're not limited by what we can plug in. We can plug in anything we want. So this is true for the sine and our cosine graph. The domain is all reals, or you can say negative infinity to infinity. Our range, in other words, our outputs, are from -1 to 1. And we also note that these functions are periodic with a period of 2 pi. In other words, the sine of x plus 2 pi is equal to the sine of x, and the cosine of x plus 2 pi is equal to the cosine of x. All right, one other distinction that I want to make, sorry about that, between these two functions. Okay, what I want to point out is that our sine function is an odd function. Now, you may or may not recall what odd functions are, but they're functions that are symmetric about the origin. And in college algebra, probably your most famous odd function was the cubic function. So notice that if we were to take our graph of our sine function and first reflect it about the y-axis and then the x-axis, we would have a mirror image. Or similarly, we could have gone about the x-axis and then the y-axis. But the point being that when you have an odd function, one property that you have is that sine of negative x is negative sine of x. Okay. Now, on the other hand, my cosine function is not an odd function. I claim it's an even function, which means that it's symmetric about the y-axis. And probably your most familiar even function is our general quadratic y equals x squared. Okay. And the cool thing about this is when you have an even function, you have that the cosine of negative x is the same as the cosine of x. In other words, whether you move over this distance to the right or the same distance to the left, your function values are going to be the same. Okay, so these are some pretty amusing properties. Now, the one last property that I would like to mention is if you look at these two graphs side by side or one on top of the other, as the case may be, one of the other things that you can note is that if we took our sine graph and we shifted it to the left, pi over 2, okay, we would have our cosine graph. Or you could similarly think of it as if you take your cosine graph and shift it to the right, pi over 2, you would be on your sine graph. Okay, so these are these two functions, and we know this also by looking at our unit circle, are just translations of each other. All right. So knowing what your sine and your cosine graph look like are essential. And from there, what we're going to do is just expand our knowledge a little bit more. For example, what if I wanted to graph y is equal to 2 times the sine of x? Okay, what would this affect? Well, again, I'm going to put my unit circle right here. Get it going here. All right, so I can then plot my points. And if I have x is equal to, or excuse me, if I plug in 0 for x, the sine of 0 we know is 0, and 2 times 0 is still 0. Now, if I go up to pi over 2, I know the sine of pi over 2 is 1. So instead of being up at 1, I'm up at 2. Notice if I'm looking at, let's say f of x is equal to the sine of x, what we're really looking at is 2 times our function. And we know that when we take a number times our function, what that does is it vertically stretches it. Okay. So again, we can then move to pi, which is 0. And now at 3 pi over 2, instead of being down at -1, we're multiplying that by 2. We're going to be down at -2. Okay. So what did this 2 in the front do? What it did is it affected the range of this particular function. Note these are never drawn to scale. Pi over 2, pi, 3 pi over 2, and 2 pi. And we can go off in this direction as well. Sorry about this. So notice that what we've done is we've vertically stretched our graph. Oopsie. All right. So in a similar manner, what if I had us graph y equals -3 times the cosine of x? Well, now what we can think of this is as follows. If my function is the cosine, aren't I taking -3 times my function? And from our college algebra classes, we know what that does. What this does is it vertically stretches it by 3. But remember, when you have a negative in front of your function, what that does is it reflects it about your x-axis. So it's vertically stretched by 3. And it's also reflected about your x-axis. So this is where your memory of college algebra and the graphing can really come in handy. So I could even just say, okay, let me take my old cosine graph. Here, hold on 1 second. I'm going to pause this for just a moment. All right, so what we can do is we can take our cosine graph and put them right by each other. And what do we see? First off, one thing we see is that the tick marks on the same are the same here. Okay, but notice that now I'm going up to 3 and down to -3. Okay, and I'm reflecting about my x-axis. So now I'm at -3, 0, 3. Okay, so you always want to use what you already have just to make your life easier. So notice this is our basic cosine graph. However, it's reflected and it's stretched. All right, so in general, what I want to get at is as follows. If you have y equals a times the sine of theta, or y equals a times the cosine of theta, a is called your amplitude. That's how high or low it goes. Okay. Another thing that I want to point out is on any of these graphs that we've done thus far, notice we have midline. Our midline is essentially the center value. And with our general sine and cosine, it's always equal to 0. However, we know vertical shifts can happen. So I'm just going to give you another definition real quick and say that the center value of a sinusoidal function is called the midline. That's your shift up and down. And so we can say that f of theta sine theta plus k, or f of theta is cosine theta plus k. Y equals k is your midline. I just think of it as my vertical shift, but one of the things that you're going to note is that the book talks about the term midline, and I want you to know what it means. All right, a couple more things we need to do here in order to move through our graphing. We just looked at y equals 2 times sine x, but now one thing that we can do is we can ask ourselves, well, what happens if we want to graph the sine of 2x? Notice now we're not taking 2 times that function value, okay? So one thing we could say is, well, plotting point sure worked well before. Let's see what happens here. I can plug in 0 for x. The sine of 0 we know is 0. Okay, our next value is typically to take pi over 2. If I plug pi over 2 in here, then I have the sine of 2 times pi over 2, which is the sine of pi, which is also 0. Okay, a bit of a head scratcher. Well, the next value we typically take is pi, but if we plug pi in here, then what we're looking at is the sine of 2 pi. And we also know that the sine of 2 pi is 0. Now, clearly putting a 2 here is not going to make it a constant function, which is certainly what appears to be going on here. So we have to ask ourselves, what will this look like? And I'm going to pause the video for just a second. All right, so since we know this is not a constant function, we've got to ask ourselves, what is going on in between 0 and pi over 2? Well, another common angle that we have is pi over 4, okay? We know what the sine of pi over 4 or 45 degrees is, but look, check this out. If I plug in pi over 4 for x, I'm really then looking at the sine of pi over 2. And the sine of pi over 2 is 1. Whoa. So this gives us some information here, okay? If I then, so I've got 0, I've got 1 pi over 4. This is 2 pi over 4. I can look at 3 pi over 4, right? Which is in my second quadrant. And if I take sine of 2 times that, well, what I'm really looking at is the sine of 3 pi over 2, which I know is -1. Now, I realize this is out of order in terms of our graph here, but check this out. Here's 0. Okay, normally we have the tick mark pi over 2 pi, 3 pi over 2, and then 2 pi. But what's happening here is I need to start looking Okay, notice 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. So we could do 7 pi over 4, and then we're back at 2 pi. Now, what happened is as follows. My range is the same, but what has happened now is that my period has changed. In fact, you can think of this as like an accordion. Now, instead of my period being 2 pi, my period is pi. So what used to take 1 full sine wave, we now have 2 full sine waves, and we can keep graphing this in the negative direction as well. Okay, so what I want you to note is that the period changed. My period here is now pi. Okay, so we could ask what relationship that sort of thing has. And I know I'm going through a lot of examples, but I simply cannot stress enough how important this really is. Okay, one of the things that you'll see here, now instead of taking the sine of 2x, I'm going to take the sine of 1/2 x. Again, I can plug in 0, I'm going to get 0. Our next common angle was pi over 2 that we would plug in. But now here, notice I'm taking 1/2 times that, and the sine of pi over 4 is root 2 over 2. Now, if I take pi and plug that in, well, really what I'm looking at is the sine of pi over 2, which is 1. So what we're seeing here, if you keep taking more and more values, is that now my period has changed to be 4 pi. Okay, so for example, I can take 3 pi over 2, but what I'm going to get here again is root 2 over 2 because I'm taking the sine of 3 pi over 4. If I plug in 2 pi, 1/2 times 2 pi, I'm taking the sine of pi, which is -1. Okay, so if I was to graph this, again, I'm up at 1 and down at -1. But here I have pi over 2 pi, 3 pi over 2, 2 pi. Notice here, what I'm doing is I am completely stretching out. So this is still, so here we have 0 at pi. We're up at 1. At 3 pi over 2, we're up at root 2 over 2. At 2 pi, oops, excuse me, that should be 0. And then I have 5 pi over 2. I'm down at -1. Oopsie, sorry about this. Not used to stretching my graphs so much, etc. Okay, so the moral of the story is if you have the sine of some beta x or the cosine of beta x, your period is 2 pi over whatever that value is. So up here, our period is 2 pi over 1/2, aka 4 pi. All right, and if that's not enough, let's talk about this. In general, we're going to have one more to go after this, but so far, if you have f of theta is a times the sine, oh, I don't want to call it theta, I'm going to call it t. beta t plus k, or f of t is b times the cosine of beta t plus k. We have A as our amplitude. That's our vertical stretch. Beta is essentially our horizontal stretch, if you will. But the key thing to note is that our period is 2 pi over that value. And K is your vertical shift or your midline. Okay, it's a lot, but you don't have to have this memorized. So please keep that in mind. All right. So suppose I told you this. Suppose I'm telling you that my sine graph goes through 0, 3. I have an amplitude to be 2. And my period is 4. What I want us to do is I want us to write an equation for this graph. Write a formula. Okay. Now we know that typically our sine goes through 0, 0. So from here, that gives us k is equal to 3. Okay. We also know that a is equal to 2 because I'm given my amplitude. We know our period is 4, which is 2 pi over whatever this value of beta is going to be. Well, we can certainly solve this for beta, multiply both sides by that. So I'm going to get beta to be equal to pi over 2. So the equation of this particular function is 2 times the sine of pi over 2t plus 3. All right. So we've done vertical stretch, horizontal stretch, vertical shift. Guess what's next? A horizontal shift. So one more horizontal shifts. Okay, so just to sum it all up, there's 2 different ways we can write this. And it can be sine or cosine, beta t minus h plus k, or f of t, a sine cosine beta t minus r plus k. Now, you might ask, what is the difference between these two? Notice here, nothing's factored out. Here, my beta, the number in front of my variable, is factored out. So, okay, amplitude is still A, midline is still K. My period is still 2 pi over this value of beta. But when your value is factored out, H is your horizontal shift. And when it's not factored out, this implies that technically you would have to factor it out, or you could just say this divided by beta is your horizontal shift. And this is as full as it gets. So what I'm going to do now is work through about 5 different examples, kind of putting all of this stuff together. Okay. So my first example is actually in the book. What we want to do, and you can look at this in the back of your section 6.1, is we want to determine the amplitude, midline, period, and then find a formula. Okay, we want to do that for this graph right here in number 5. Okay, well, notice the midline, the middle of my graph, is at -4. Okay, so I see that my midline is -4. I'm just going to write all my relevant information here as we're looking at our graph. Okay, now what is my amplitude? If this is kind of the center, notice we're showing that this is shifted down 4. But if we look, we see that from that center, it goes up 3 and down 3. So my amplitude is equal to 3. And now what we need to ask ourselves is, what is our period? Well, notice we could say that we start the sine wave here. Notice I said it's sine already, and I'm saying sine because it's centered at 0 right here. Okay, so I go up and then down. So notice my period here is 2. 2 is where I've done a full sine wave. So if my period is equal to 2, well, I know that my period is 2 pi over whatever that value is in front. And therefore, of course, beta is just going to be pi. So the equation of this function is 3 sine of pi t minus 4. Okay. All right. Now the next one, we don't have to look at a graph, but what we are going to do is I'm going to give you the equation of a function, and I want us to find various things. So what if I say that y is equal to 3 times the sine of 8x plus 4 plus 5? So I want us to find our amplitude. I want us to find our period, the midline, and the horizontal shift. All right, so using our formulas that we gave, we can just totally decipher this. Notice we're in the top version because our 8 is already factored out. So our amplitude here is 3. My period is 2 pi over whatever is in front here, 8. So in other words, in this case, my period is pi over 4. My midline is the line, horizontal line y equals 5. And my shift is 4 to the left. Notice it's to the left because I'm adding in there. All right, let's do this one. Similar, but now we're going to say y is equal to the sine of pi over 6x plus pi minus 3. The difference here is that I didn't factor out my value beta. Okay, so now we're in this situation right here. All right, well, my amplitude is 1. Notice it's just a 1 right here. My period is 2 pi over the number in front of my variable. So 2 pi divided by pi over 6 is times 6 over pi. So my period is 12. Let's see. My midline is the line y equals -3. And in terms of my horizontal shift, since I did not factor this value out, notice you take this value divided by this value. So pi divided by pi over 6. My horizontal shift is 6, and again to the left because I'm adding in here. All right. So the next two we're going to look at again are graphs in the book. And you notice that when I'm actually trying to get a function from a graph, I don't even try to replicate the graph freestyle by hand. Okay, I know my limitations for sure. Okay, so I want us to look first at number 17. What we want to do is we want to find a formula for this function. Okay. All right. Well, what do I note? I notice that the midline is 0, right? Okay. But I also see that I have an amplitude of 4. I'm taking notes on the side while I'm analyzing this graph. See, amplitude is 4. Okay, it's centered here. All right, and what else do we have? Well, we've got to notice how much is one period. So for example, if I want to start right here and see how long it takes me to go one full sine wave, well, it goes from -1 to -11. So I'm going to have my period is equal to 10. We'll figure out what corresponding value of beta gives us that. But notice then we're also shifted because our sine graph typically goes through 0, 0. And I claim here we're shifted to the left 1. All right. And I notice that it's a sine wave. We could have written this as a cosine, but notice then we would have shifted it to the right. Okay, so y equals 4 times the sine. All right, my period is 10, which is 2 pi over beta. So 10 beta is 2 pi, or beta is pi over 5. And then if I'm shifting left 1, I'm going to write it as a factored out. Ooh, excuse me, shifted left 1. I'm going to add 1 in there. All right, one more of these guys. Now what we're going to do is we're going to look at number 19 and do a similar thing with this. Okay, but now I'm going to say, well, listen, I do a lot of things with the sine. Let's do a cosine guy. Okay. So I'm going to think of this as a cosine function, and I'm going to need to take into account what the shift is. But notice it's centered at 0, so I'm not shifting up or down. The amplitude is equal to 1, which is sweet. Okay. Now my period, well, we've got to ask ourselves, where do we go one full sine wave? Okay, well, notice, or a cosine wave, either way. Notice if I start here between -4 and -5, I'm at 0, and I go there, and then it goes to 5, between 5 and 6. Ha! So again, this is a fluke. My period is equal to 10, if you count that out. So from that, we know beta is equal to pi over 5. And then also we see that normally we would be up here. We've shifted it to the left too. So now if we think of this with our cosine, we have the cosine pi over 5 times the quantity x plus 2, since we're moving to the left. All right, sorry for all those pauses in the middle of the video. That's what happens when you have a cat, I suppose. All right, I hope this helped. Thanks.